So, welcome to today's session in which we are going to discuss one of the beautiful topics, that is central limit theorem. So, first we will see what this central limit theorem says. So, as mentioned here, suppose if x bar is the mean of a random variable of size n which we have taken from the population, and the mean of the population is mu and the variance is sigma square, then the central limit theorem says z equal to x bar minus mu by sigma by root n is a random variable which follows or which approaches the standard normal distribution when n is large, n is very large, that is n tends to infinity. So, the importance of this theorem is, here if you see in the entire discussion, there is no information, there is no clue regarding the nature of the population. Right? So, here there is no clue about the population, whether the population follows binomial distribution, Poisson distribution, normal distribution, etc., etc. So, even then what we are using is, we are using the standard normal distribution. So, that means irrespective of the nature of the population. So, whether it is normal or Poisson, binomial, anything like. So, we can convert or we can use standard normal distribution when the size of the sample is very large. Now, for example, I will take as a population here. Right? So, I take the population which is very large. So, like n tends to infinity. So, this population, it can be normal population, or it can be a population which is of binomial nature, or this may be Poisson also. So, then or it may be there is no clue regarding the nature of the population. Now, here we will take a sample of size n and size n1 here, where we can find its mean as well as its variance or standard deviation. Similarly, we can take another sample of the same size whose mean is x2 bar and whose standard deviation is s2. Similarly, we can take samples of the same size, and for every sample we can find its mean as well as variance or standard deviation. Now, if we see this we can define a random variable x bar which takes care of the distribution of means of the samples. That is what we call this as, this x bar is defined as a normal random variable which is associated with distribution of samples. That is, simply we can say that this is sample distribution. Right? Now, if we consider this x bar and this is a random variable, so where we can try to find the mean of this random variable, that is we can write this as mu x bar, and similarly this is a random variable whose variance or standard deviation we can have, that is we write this as sigma x bar, standard deviation. That is, mu x bar is mean of the normal random variable x bar. Similarly, this is the standard deviation of the random variable x bar. Now, this by using the central limit theorem, we can conclude this mu x bar equal to mu, that is the mean of the sampling distributions is equal to mean of the population. Similarly, the standard deviation of the sampling distribution sigma x bar equal to sigma by root n, where sigma is the standard deviation of the population and n is the size of the sample. So, if we summarize the central limit theorem and its importance, like, so central limits theorem allows us to use the standard normal distribution irrespective of the nature of the population. So, where we can use z equal to x bar minus mu by sigma by root n irrespective of the nature of the population. That is why this is a very important theorem in many of the applications which we are going to see in the subsequent sessions. Thank you.